Hi everybody, today we're going to talk about how Lewis structures can be used to figure out the ionic compound that would form between a metal and a nonmetal. So we're going to start with, for example, sodium and chlorine, or table salt. So sodium is in, if we look at the periodic table, we can tell that sodium is in this family here, which means it has one valence electron. Chlorine is in this family here, so it has 7 valence electrons. Remember the pattern was 1, 2, skip the middle, 3, 4, 5, 6, 7 valence electrons, and then full outer ring. So chlorine has 7 valence electrons. So both of these want to become stable in an ionic compound. And so we're going to do that by having Na will give away or lend its 1 valence electron to chlorine. Now sodium feels like, let me stand on this side. Now sodium feels like it is stable because it lost this electron. And remember, underneath, there's another energy level that would be full. And now chlorine has 8 in its outer ring. So they both feel stable. Let's now look at another example. Beryllium and oxygen. So beryllium is in the second family, the alkaline earth metal family. So it has 2 valence electrons, where oxygen family is in the 6th family over, and so it has 6 valence electrons. So if beryllium were to give away these 2 electrons, its next ring down would be full, and so that's what this beryllium atom would do to become stable. It will give 1 electron into that spot for oxygen and 1 electron into that spot for oxygen. Okay. So that means that these 2 compounds both work on a 1-to-1 ratio, which means I only needed 1 sodium to satisfy what chlorine needed for them both to feel stable. So therefore the compound would be written like this. Same thing here. I only needed 1 beryllium to meet all of what oxygen needed. Where, for example, if I wanted sodium and oxygen to bond, it still can happen. Let me show you how. Okay, so here we've got sodium and oxygen. So sodium could give its 1 electron there, but sodium's stable now, but is this one stable? No, it's not. So I'm going to need another sodium atom with its own original 1 valence electron. Now that valence electron could be transferred to the oxygen, and now they both feel stable. Here's the compound formula, is that we needed 2 sodium atoms to give their electrons to oxygen in order for each sodium to feel stable and the oxygen atom to also feel stable. So here we have sodium oxide. Let's look at another example. All right, let's do Mg and nitrogen. So magnesium has 2 valence electrons and nitrogen has 5. I know that because of what column they are on the periodic table. Magnesium is going to want to lose electrons. Sodium is going to want to gain electrons. So let's see how these 2 can form a compound. Well, this electron could fill that empty space. This electron could fill that empty space. But, the nitrogen's not stable yet. So I must need another magnesium. Okay. Now when I draw it with its own 2 original valence electrons. So here 1 valence electron could go into that spot Now this nitrogen atom feels like it has 8 valence electrons in its outermost energy level, so it is stable. This one's stable because it got rid of those 2, allowing the energy level below to be stable. But this magnesium still has 1 too many electrons. So I'm going to need another nitrogen atom with its own original 5 valence electrons. That was a 5, by the way. 5 valence electrons. Okay, so that electron could go into that spot. But nitrogen's not stable. Now, often my students ask me this at this point, say, is this just going to go on forever? Is this ever going to end? And I said, yes, keep going, it will end. So since the nitrogen is not stable, we'll need another magnesium. That magnesium has its own 2 starting valence electrons. Those electrons can then fill up the empty spaces on the nitrogen. Oh, it's done now. It's done. This magnesium was able to lose all of its electrons. This nitrogen got the ones it needed. It's stable. This one's stable. That one's stable. That one's stable. All right, so what is the ionic compound? Well, in order for it to work, I needed 3 magnesiums. So I'd write Mg3, and I needed 2 nitrogens. Mg3 and 2. Now, if you ever noticed in ionic compounds, when we name them, we don't say the number in the name, the number of each atom. We would just name this magnesium nitride. Okay? We don't have to say the number because anybody who understands basic chemistry would know that the only way magnesium and nitrogen could form a compound together and the compound be stable is if it's like this. And so we don't need to say in the name how many of each atom because it already tells us just because there's only one possible answer. Okay? When you learn about covalent compounds later, in those compounds you do have to tell in the name how many. That's why we say carbon dioxide. It's because we're telling the person that there's 2 oxygen atoms in that compound. Because there's other possibilities. So ionic compounds, we don't have to do that. We just name the metal first, the nonmetal second, and then change the ending to IDE. So I hope this helps. If it helped you to understand how we can use Lewis structures to illustrate ionic compounds and how to figure out what that compound must be, please give the video a thumbs up and subscribe to find other videos like this. Teachers, there is a resource that you can use to help your students further practice this activity. Have a great day.